This is Solubility Product and Partition Coefficient presented by the SHRTV with reference International ASA Level Chemistry by Laurie Ryan and Roger Norris. So we start with the equilibrium and solubility. So we need to know that we learned that most ionic compounds dissolve in water, and we related solubility to enthalpy changes of solutions. So now some ionic compounds, however, are insoluble or only slightly soluble in water because of what? The reason is because of their ionic crystals. We have already seen how ionic crystals are oriented. So the chapter on ionic crystals. So now different molecules have different ionic crystals, different bondings with their corresponding cations. So different metallic ions have their corresponding anions. So sodium chloride is regarded as a soluble salt, but now we need to know that what in cases, there are certain cases normally sodium chloride is a soluble salt, but there are certain cases where sodium chloride can become insoluble. Let's take an example. We need to know that what if you take a certain big bunch of table salt that you have at home. If you take a big bunch of table salt at home and then you place a small pinch of water, the question I'm going to ask you is all of the sodium chloride going to dissolve in that pinch of water? The answer is no. And this answer is no. Why? Because the water, so sodium in that case, is extremely concentrated with respect to that water. So since it's extremely concentrated, most of the sodium is not going to dissolve in that water. So that's the point. So now that's why here we see that in extremely saturated solution contain this. So in 36 gram per 100 gram of water, that's going to be soluble. But when it is more than that, it's not going to be soluble. Lead chloride is regarded as an insoluble. It's a saturated solution. So that's why in this case you see only 0.99 grams of lead is going to be insoluble in 100 grams of water. So now let's see the solubility product. So that's why all of this making all this difference in grams, the mass of the salt that's going to be necessary for it to dissolve inside the water, all of that making into account for what is called the solubility product. So now let's see the solubility product. A solubility product actually is the equilibrium constant of a reaction which is going to show the dissolution of a molecule. So example, silver chloride dissolves to produce an aqueous solution of silver ion and chloride ion. Now the solubility product actually is the equilibrium constant. What's the equilibrium constant of this reaction? This equilibrium constant is going to be Kc is equals to the concentration of silver ion aqueous times the concentration of chloride ion aqueous divided by the concentration of silver ion solid. Now the question is, silver ion solid is, you need to know that silver, when you see silver ion solid and you see water as being concentration, as written in concentration, you need to know that the concentration of silver ion solid or any solid is only given as 1. The concentration of silver ion solid or any solid is given as 1. The concentration of water is given as 1. The concentration of a gas is given as 1. The concentration of gas instead now is not given as 1. Here for gas we instead calculate for the partial pressures, and the relation between the Kp, which is the partial equilibrium, the equilibrium constant related with partial pressures, is equals to Kc, the concentration the Kc in bracket RT raised to the power delta N, where delta N is the change or the difference in the number of moles of the product and reactant. So now this is going to be a KSP. So when you have since silver chloride is equals to 1, we have this going to give the KSP as being equals to concentration of silver ion times the concentration of chloride ion. So this is called the equilibrium for the solubility product. So solubility product is a product of concentration of ion in saturated solution of sparingly soluble salt at 293 Kelvin raised to the power of their relative concentration. So it's only the equilibrium product. Try to define try to give the definition of equilibrium constant, because you know that the equilibrium constant is defined as the product of the products raised to the appropriate power divided by product of condition of the atom. But now we just say the product of the products at a temperature of 298 Kelvin for a sparingly soluble salt, for a soluble salt, as easy as that. So now so this is what you have to know. So that's why you say KSP is going to be the concentration of A, and that depending on if it has depending on their values on the stoichiometric equation. So this is the same here. So when you have these molecules splitting into that, you have now the KSP given as a concentration of iron 2 iron times 2 that sulfide ion or raised to the power 3 and all that. For magnesium ion is going to be given as this, and now you need to know that the unit of the KSP will also vary as a unit of equilibrium constant depending on the amount of moles, the amount of mole fraction, or the amount of the raised powers that different salts have in different ions have in these solutions. So now you need to know that the KSP are constant for particular solution. Example, silver chloride has a particular KSP, aluminum hydroxide has a particular KSP, barium carbon has particular KSP. So if you want to see their KSP, just pause the video and then you see their corresponding values. So let's take an example. Calculating the solubility product for solubility. Saturated solution of magnesium fluoride has solubility of this. Calculate the solubility product. So they have told you that saturated solution of magnesium fluoride has solubility of this. So this is what is dissolved. So now we calculate the solubility product of magnesium fluoride. So in order to calculate this, you know, say that when 1.22 times that dissolve in 1 dm cube, so moles, you are going to have magnesium. So you see that what? You see that this magnesium fluoride is going to produce 1 mole of magnesium ion and 2 moles of fluoride ion. So this is why the concentration of magnesium is going to be this, and the concentration of fluoride is going to be 2 times the concentration of magnesium fluoride. So now, since you have this different concentration, now you are capable of calculating the solubility product, and the solubility product is the concentration of magnesium ion times the concentration of fluoride ion raised to the power 2. So when you are going to calculate it in step 3, this is the formula that you're going to have. This step 4, now you can calculate by multiplying each of them, and then you're going to have your answer. Don't forget to put the unit, because this is in mole per dm cube and this is in mole per dm cube, always a power 2. The total of unit is going to be mole cube dm negative 9. So your answer, this is your answer with its unit. So now the next question is calculate the solubility product and all that. So you already know. So calculate the solubility from solubility product of this molecule of copper sulfide. You need to know that what copper sulfide is as such like that. So you have now the solubility product K. You need to know that. So in this, the formula is going to be KSP is equals to the concentration of copper ion times concentration of sulfur ion. So this is what's occur. So now they ask you to calculate the solubility, of this molecule. When you want to calculate solubility, you need to know that what in this particular reaction, copper ion is going to be equal to sulfide ion. Since copper ion is equal to sulfide ion, so what they're going to say, you can now substitute it into this equation. So you say KSP is going to be the concentration of copper ion all squared. So now when you substitute, you are now going to say that copper ion is going to be the square root of the KSP. So you just find the square root of KSP and you have the answer. The next subtopic is going to be predicting the precipitation. So you need to know that solubility product can be used to predict if a molecule is going to precipitate or not. So now let's say solubility product, you need to know is the number for this barium carbonate is given as 5.5 times 10 to the power negative 10. So now we need to know when that molecule is going to precipitate or not. So this molecule here is going to be precipitating if you increase the solubility product. Let's visualize. Let's take some example. Will a precipitate form if we mix an equal volume of solution of 1.0 times 10 to the power negative 4 mole per dm cube of this and this? So now in this case, what happens? You see that you have the concentration of barium ion. So you need to know that this barium chloride is going to produce this. So if you have an equal concentration of this and this, Barium chloride, you are going to see that it's going to produce. So in this question, when you have this different molecule, in order for you to find if it's going to precipitate, just find the solubility product that the two molecules are going to form. Normally barium is going to, the solubility product normally is soluble when it is 5.5 times 10 to the power -10. But now if the solubility product is greater than this normal, if the equilibrium product calculated for this question is greater than the solubility product, then the molecule is going to precipitate. So in this case, you can see 1.0 that and that of barium. So you see that barium ion is going to be 2.5 times 10 to the power -5. Carbon is going to be that. When you multiply, you're going to have the solubility, the new equilibrium constant to be this, but this now is going to be greater than this solubility product. This is why this solution is going to be insoluble in water. So now the next one is a common ion effect. Common ion effect is the reduction of solubility of a dissolved salt achieved by adding a solution of compound which has an ion in common with the dissolved salt. So in this case here, what are you going to visualize? An example of common ion effect can be seen when you add a solution of sodium chloride to a saturated solution of silver chloride. So when you add sodium chloride and silver chloride, so when they have a particular common ion, so that's what. So the reduction in solubility of a dissolved salt by adding a common ion between by adding a solution that has a common ion with that salt is going to be common ion effect. So example, we said that when you have this sodium chloride and you have silver chloride, you have again the reduction in solubility of silver chloride because you have added sodium chloride. So that's now you see. We now add solution of sodium chloride. We first have silver chloride, it has dissolved. We now add solution of sodium chloride. The chloride ion is common in both sodium ion and silver chloride, sodium chloride and silver chloride. The added chloride shift the position of equilibrium. In this case, it's going to shift the position of equilibrium to this direction. Silver chloride is going to be more precipitated. The addition of the common ion, we have chloride has reduced the solubility of silver chloride because the solubility product is now greater, because when you now find the new solubility product is going to be greater. So that's the case. So we have visualized everything involved with solubility product. Now let's go to partition coefficient. So on partition coefficient here, we just know that a solid is going to be, let's say that a solid has both the solubility ability in two different solvents. Let's say that a solid is capable of being dissolved in two different solvents. The partition coefficient is just defined as a constant. Kp is being equals to the concentration of that solution, the concentration of the solvent inside the organic solvent, and divided by the concentration of the solvent inside the polar solvent or water. So just say concentration of that solution inside organic solvent, example ether, divided by concentration inside water. That's going to give you the partition coefficient. So from here we have seen everything involved with so the last part is going to be paper chromatography for partition coefficient. You need to know that paper chromatography, you use a chromatographic paper in this case. So you use a chromatographic paper, and that is going to separate different moisture, and this is because of partition coefficient. We need to know that on the paper, certain molecules have the ability to that different molecules have different ability to dissolve with water, and they have different ability to also dissolve into the chromatographic paper. Since they have this different ability to dissolve both in water and the chromatographic paper, you are going to have different partition coefficient of those molecules. So now your level of rise on the chromatographic paper is going to show your partition coefficient, and thus if you use for the identification of particular molecules. So there we have seen everything involved with solubility product and partition coefficient. So say thanks for your kind attention. Please don't forget to like and subscribe for the channel. Thank you.